All right, welcome back, class. This is week 12's Wednesday's lecture, part 1. We're going to be continuing with chapter 6. So the last thing that we did is we did a problem where we looked at a space probe taking off from the moon Dysnomia, which is one of our dwarf planet Eris's moons, and we used the relationship between gravitational potential energy to find out the mass of the planet by looking at how much the gravity from that moon would slow down the probe. And by that I mean the mass of the moon, not the mass of the planet. So this had two interacting objects. Now let's take a brief look at what a system looks like where we have more than two objects. So building on our example, where we had Dysnomia, the moon, we had the space probe taking off, and now let's look at a 3-particle system so we can add in the dwarf planet Eris. Because Dysnomia is, of course, orbiting around Eris. So in this case, we have 3 objects. We've got our probe that has mass m. We have Eris, which has mass capital E sub e. And we have the mass of Dysnomia, which has mass capital E sub d. All right, so how many pairs do we have? So each one of these objects will have potential with the other 2. So that makes a total of 3 pairs of objects. So the total potential for this system, U, is equal to minus G, mass of Eris, times the mass of the probe, divided by the radius to Eris from the probe, plus minus G, mass of Dysnomia, mass of the probe, divided by the radius to Dysnomia, plus minus G, mass of Eris times mass of Dysnomia, the radius of Eris to Dysnomia. And of course, that's center to center distance. Now, when we're looking at a problem like this, we'll want to think about the change in potential energy over the interaction. So we're still dealing with a situation where we have a probe that is leaving Dysnomia, so it's going to be on a planetary time scale, a relatively short span of time. So we could assume that for the length of time that we're looking at, Dysnomia and Eris are essentially fixed in space, and therefore if we're looking at the change in potential energy over this interaction, this is going to stay the same. The mass stays the same for each object, and that distance between them is going to stay the same. So if they're just hanging out, not really moving over that time span, then any change is going to be 0. All right, so that's a question you also want to ask yourself. Are there some zeros that are the result of the interaction time that I'm looking at? All right, so I'll write a note here. Assume Dysnomia and Eris fixed. So U with the pair of dE, or delta U with the pair dE is equal to 0. So they do have potential energy between them. It's just not going to change at that interaction. So now let's set up our energy principle. Okay, so energy is going to, or delta E is going to be equal to the change in kinetic plus the change in potential And this is, of course, equal to any work done. Now, for this particular segment, our work is equal to 0, and we're dealing with a classical system, so there's nothing in the surroundings. Okay, so we're just going to focus on this part of the equation. So change in kinetic energy for this probe taking off, being slowed by dysnomia, is going to be equal to 1/2 mv squared, or the change in 1/2 mv squared, plus the change in minus g mass of Eris, mass of the probe, divided by the distance from Eris to the probe, plus the change in potential from minus g mass of dysnomia, mass of the probe, divided by the distance from the probe to dysnomia. And all of this is equal to 0 as there is nothing to do any work on the system. So this is why setting up a clever choice of system and surroundings is useful. Sometimes you can set things equal to 0. I'm a big fan of that. Okay, so we can set this up so that we have 1/2 mv final squared plus minus g me, the mass of Eris, over the distance to Eris final, because it's going to change, plus minus g, the mass of dysnomia, times the mass of the probe, divided by the distance to dysnomia final. And because that's equal to 0, we're essentially just moving initial and final over to each side. This is all equal to 1/2 mass of the probe times the initial velocity plus minus g mass of Eris times mass of the probe, divided by the distance to Eris initial, plus minus g mass of dysnomia, mass of the probe, divided by the distance to dysnomia initial. So there is no change of identity. The masses are going to stay the same throughout the entire time, and then you could just plug and chug along and solve this problem. So in this case, we're not actually going to solve it. The point of this was just to show you how to set up a 3-particle system and all the parts to think about. So if you want to, you could go ahead and solve this on your own. All right, speaking of doing things on your own, show why delta u y is approximately g m delta y near Earth's surface. So this is something that we have stated before, and this is a really easy and fun little derivation to do. So it's not a proof, it's a derivation. So you want to start from delta G M1 M2 over R, the gravitational potential energy between the Earth and the object. All right, so and I wanted to say one more note. Make sure that when you're doing these types of problems, look at what the question is actually asking for. Sometimes they're just asking for you to set up the energy equation, and then you get to stop. You don't actually have to solve it, you just need to set it up. And we are going to do a couple energy equations that are really too complicated to solve, but relatively straightforward to set up. All right, so let's do some near-Earth examples of potential energy, as that is the most relevant to your everyday interactions. Okay, so we have a 400 kilogram zebra stands on the ground. And we want to know U of a system of zebra plus Earth. So standing on the ground. And then we'd like to know what would happen if the zebra jumps over a bush that's approximately 0.75 meters high above the ground. Then what would delta U be from A to B? So from part B to part A. All right, so in the initial state, so notice we are not looking for change in potential. We are just looking for potential as it stands. So we are always 1 Earth radius away from the center. So the potential due to gravitational attraction between the zebra and the Earth is equal to minus g, mass of the Earth, times the mass of the zebra divided by the radius of the Earth. By the way, this is how much potential you have with the Earth right now. Plug in your mass in place of the zebra and the radius of the Earth, and you've got it. So the gravitational potential for this setup is equal to minus 6.7 times 10 to the minus 11 Newton meters squared over kilograms times 6 times 10 to the 24 kilograms, the mass of the Earth, times 4 times 10 to the 2 kilograms, the mass of the zebra, divided by 6.4 times 10 to the 6 meters, the radius of the Earth. So here is what we've set up. And I'm going to go ahead and move to the next sheet of paper. The gravitational potential energy between these two objects is equal to minus 2.51 times 10 to the 10 joules. All right, so for part B, we want to look at delta U. So delta U, as you will have derived on your own near Earth's surface, is basically mg delta Y. So this is equal to 400 kilograms, the mass of the zebra, times 9.8 newtons per kilogram, times 0.75. The zebra has gone up, so therefore Y is positive, and delta U is equal to 2,940 joules. And the implied new potential would be minus 2.51 times 10 to the 10 joules plus 2,940 joules. So really, the bulk of your potential at any given moment from the Earth is more dictated by how far away you are from the center of the Earth, which is why Earth problems tend to focus on change in potential instead of calculating the potential in that moment. So, for systems near Earth with Earth in the system, the energy principle often looks, now remember, we're just rewriting a classic principle like this. So K final plus mgy final is equal to K initial plus mgy initial plus work. By the way, this is a very good equation to memorize if you have a standardized test in your future with physics equations. So this is what typically you're looking at for a near-Earth system. All right, so let's do another example, just to really drive this point home. So we have a ball falling with a speed of 7 meters per second with position 42 meters above surface. How fast is it falling at position Y equals 28 meters? Neglect air resistance. And use the energy principle. Okay, so let's set up our problem. We have our system, which is going to be the ball plus the earth. We want to take advantage of that gravitational potential, so we need both objects in the systems. We also want nothing to do any work on the ball. So that puts nothing of interest in the surroundings. We have our initial state, where the speed is equal to 7 meters per second, 42 meters above ground. And our final state, which is 28 meters above ground. All right, so using the energy principle, remember that's just my notation. Kinetic energy final plus potential energy final is equal to kinetic energy initial plus the potential energy initial plus any work done. So the first thing we want to do is find some zeros, and I just see one. We know that there's nothing in the surroundings to do any work, so therefore work must be 0. So we can go ahead and flesh this out. So we have 1/2 mv final squared plus mgy final is equal to 1/2 mv initial squared plus mgy initial. All right, so we see that we've got a mass in each part of the equation, so we can go ahead and cancel that out, which is pretty useful since we don't know the mass of the ball. And it turns out we don't need to. And what we're actually trying to solve for, of course, is V final. So let's go ahead and algebraically rearrange to solve for V final. So V final squared is equal to VI initial, or V initial squared minus 2G y final minus y initial. And so V final is equal to the square root of 7 meters per second quantity squared minus 2 times 9.8 newtons per kilogram times 28 minus 42 meters. And V final is equal to 17.98 meters per second. Let me go ahead and show that to you. All right, so pretty straightforward on how to solve these types of problems. So I will end part 1 of Wednesday's lecture here and look for part 2.